This video covers the general properties of waves and electromagnetic spectrum for AQA Core Science 1.5. Okay, so there are two types of waves, the first of which is transverse, and the key property of transverse waves is that when you have the medium, which is the thing that the wave is travelling through, it vibrates, and the direction of vibration in a transverse wave is at right angles to the direction of energy transfer, as you can see from this animation. So the yellow dot is a particle in the medium, and it's vibrating up and down, whereas the energy transfer, the direction the wave is moving in, is to the right in this case. So that's the key property. We also need to be able to label parts of a transverse wave, and the two key things you need to be able to label on the wave are the amplitude of the wave. So that's the maximum displacement of the particles in the medium. That's how far the particles move side to side at maximum. So it's from this blue center line here, which is where the medium would be if there was no wave at all, up to the peak of the wave. The second property is wavelength, and that's usually the easiest way to measure that is from one peak to the next peak. Okay, you could do it from one trough to the next trough as well. And something you can't label on the diagram is frequency. Now, frequency is the number of complete waves passing a point in 1 second, and a complete wave is one whole wavelength. So from the point up here all the way through to the next point. If that goes past, that's one complete wave. The other way to define frequency is the number of vibrations per second. And because this diagram is basically like a picture of the wave, we can't really label frequency. We'd have to look at an animation to see what frequency is. So you're never going to be required to label frequency on a diagram, just know what it is. So there's a peak. We've talked about that for measuring the wavelength, and the bottom end of the wave is called a trough. And examples, very important. Electromagnetic waves are the most common examples of transverse waves. If you're asked for an example in the exam, any type of electromagnetic wave usually will be fine as well, so any of the parts of the spectrum, and we'll come on to that later. The other example is mechanical waves in a slinky. You could also say water waves were transverse. Remember, it's really important to recall that mechanical waves in a slinky can be either transverse or longitudinal. So that's a really good example to use if you're asked for a wave that can be both transverse and longitudinal. Okay, so the next type of wave is a longitudinal wave, and here the key characteristic is that instead of being at right angles, the vibration of the wave is now in the same direction as the energy transfer. So if we look at that, you can see the yellow particle now as part of the medium is vibrating left to right in the same direction as the energy transfer. Okay. Now, what we need to look at then is how do we label some of the things on this wave. Now, we can't label as much as we could on a transverse wave, at least not easily. The one thing we can label, if we look at a freeze frame of the wave, so that's just, we've stopped it at one point in time so we can label it. We can still label wavelength. Okay. Now this time we don't have peaks and troughs. We can't label amplitude because it's very difficult to see where the little white lines that represent the displacement of the wave, where did they start off? You can't really see that. Okay, so you're never really going to be asked to label amplitude on a longitudinal wave, only wavelength. Frequency, again, exactly the same definition, we still can't label it on the diagram. So when you're measuring wavelength, the usual way to do it is between compressions, and a compression is where the particles in the medium are closest together. So you may also see this diagram, instead of with nice sort of neat lines, you may see it done with particles in the medium. If there are lots of particles drawn in one place, that's a compression. Okay, and if the particles are very spaced out, that's called a rarefaction. Okay. You could also measure the wavelength of the wave from rarefaction to the one rarefaction to the next rarefaction. That would be fine as well. And examples of longitudinal waves, sound waves, especially in gases. So sound in air is the most common example. And again, mechanical waves on a slinky. If you push and pull the end of the slinky, you will get a longitudinal wave rather than a transverse wave. Okay, so that's the two basic types of waves. Remember, waves in general, the key thing is that they transfer energy from one place to another without transferring material stuff. Okay, so if you think about the yellow dots that you've seen, whilst they move from side to side during the progress of the wave, overall they don't move from one place to another. Okay, they stay roughly in the same place despite their vibration. Okay, so we need to look in detail at one particular type of transverse wave, which is electromagnetic waves. And as you can see, the electromagnetic waves come into a spectrum that includes 7 different types, and you need to know these different types and the order in which they come. And we need to be able to relate that order to the properties you've just looked at in the previous couple of slides. So, one way to remember it, this is just a mnemonic that I use. Ronald McDonald in Venice uses extra garlic. So Ronald for radio, McDonald for microwaves, and so on. You can make your own one up to do that, that's fine. That's just a suggestion. Some people just like to remember the list, whichever suits you best. Okay, so we need to know then that the radio end of the spectrum, the electromagnetic spectrum, is long wavelength and low frequency. And this also means it's low energy. Okay, if you imagine a wave on a slinky, if you want to make a high frequency wave, you've got to move the slinky backwards and forwards very quickly at one end, which takes a lot of energy. Okay, so a lot of energy gets transmitted down that slinky when you're moving it backwards and forwards quickly. So slow vibrations of the slinky, which would be low frequency, there's not a lot of energy there. And it's the same for these electromagnetic waves. Radio waves don't carry a lot of energy. Okay, and they have a very long wavelength. The key thing to remember, you don't really need to remember the frequency, but you need to know that basically the longest typical radio waves are around about 10 kilometers. You can get longer than that, but for the purposes of the exam, that's the number to remember. 10 to the 4 meters, or 10,000 meters, or 10 kilometers. And logically, the other end of the spectrum has to be the opposite, so the gamma rays are very short wavelength, 10 to the minus 15 meters. So that's at 0 and 14 zeros after the decimal point with a 1. That's about the same size as the nucleus of an atom. So incredibly small wavelength gamma rays. And they therefore have a very high frequency and high energy as well. We'll look at the wave equation, which kind of explains why long wavelength goes with low frequency in a later video. Okay, another important thing to remember, although the number is not vital for you to remember because you should be given it, it doesn't hurt, it's an easy number to remember, is that all types of wave in the EM spectrum travel at 300 million meters per second in a vacuum. Alright, a vacuum, remember, is just sort of empty space. The only thing that can change the speed is if the electromagnetic wave travels into a different material. Again, in a later video we'll look at refraction, and that's what occurs when the wave travels into a different material. It can slow down, basically, from this speed in vacuum. But if you're ever asked a question, okay, at all about what speed waves are moving, if it's electromagnetic waves, one of the types on this list, and they don't talk about which material it's in, it will always be this same speed. You cannot change it by doing anything, okay? Now, the other thing they can do is they can be mean and they can flip the spectrum round, okay? So before we had it running radio on the left to gamma on the right. This time we've got gamma on the left to radio on the right. The exam could have it either way round. So you really must make sure you can write it down either way round and not just have it so you've got it memorized with radio on the left. And remember, don't just think long wavelength on the left, which is how we had it before. Okay, you must remember short wavelength goes with gamma rays and long wavelength with radio waves. Okay, so yeah, could be either way around. Be on the lookout. Typical questions would, on a basic level, would involve missing parts of this spectrum for you to fill in, and then questions ask you to compare bits of the spectrum. So, for example, they could ask you to give a type of electromagnetic radiation that has a longer wavelength than infrared. In which case you remember, well, there's infrared, long wavelength this end, so microwaves and radio waves would both be longer wavelength than infrared. Another useful thing to remember, most of you probably know this already, is the order of the colours in the visible spectrum. So here they are. It makes sense really that the red end of the spectrum is next to infrared, and the violet end of the spectrum is next to ultraviolet. So that's the way to remember which way round the colours go. Red at the infrared end, violet at the ultraviolet end. And then the order of the colours, usually is quoted in this order, is from the red end: red, orange, yellow, green, blue, indigo and violet. And one way to remember that is another mnemonic, which is Richard of York gave battle in vain. Again, you can make your own one up. That would be totally fine. Okay, so that's the basic properties of waves. The next video I'll move on to looking at some other properties of waves.